Hello everyone and welcome back to CS4540 week 6 video. For this week will be looking at mostly Andre Caparte videos, and these are the topics that we will be discussing in this video: hallucinations, RLHF, tokens, jagged AI, and post-training. And then we have one clip from Steve Setz called All Actions.
Want to talk to is, of course, hallucinations. So you might be familiar with model hallucinations. It's when LLMs make stuff up. They just totally fabricate information, etc. And it's a big problem with LLM assistants. It is a problem that existed to a large extent with early models from many years ago. And I think the problem has gotten a bit better because there are some mitigations that I'm going to go into in a second. For now, let's just try to understand where these hallucinations come from. So here's a specific example of three conversations that you might think you have in your training set. And these are pretty reasonable conversations that you could imagine being in the training set. So like, for example, who is Tom Cruise? Well, Tom Cruise is a famous actor, American actor and producer, etc. Who is John Barrasso? This turns out to be a US senator, for example. Who is Genghis Khan? Well, Genghis Khan was blah, blah, blah. And so this is what your conversations could look like at training time. Now, the problem with this is that
For this first clip, I chose to talk about hallucinations in large language models to outline the dangers of fully trusting these systems. Hallucinations happen when a LLM confidently generates false or made up information. For example, it might invent a fake scientific study or give a completely incorrect answer that sounds very convincing. These errors can come from several causes like gaps in the training data, vague prompts, or the model's designed to always produce an answer even when it's unsure. The biggest issue is trust. If users assume an AI says is true, these hallucinations can lead to misinformations and poor decisions. That's why understanding these limitations is so important, not to dismiss LLMs, but to use them wisely with critical thinking and proper verification.
So as I mentioned, the naive approach is if we just set infinity human time, we could just run RL in these domains just fine. So for example, we can run RL as usual if I have infinity humans. I just want to do, and these are just cartoon numbers, I want to do 1000 updates where each update will be on 1000 prompts. And for each prompt, we're going to have 1000 rollouts that we're scoring. So we can run RL with this kind of a setup. The problem is, in the process of doing this, I would need to ask a human to evaluate a joke a total of 1 billion times. And so that's a lot of people looking at really terrible jokes. So we don't want to do that. So instead, we want to take the RLHF approach. So in RLHF approach, we are kind of like the core trick is that of indirection. So we're going to involve humans just a little bit. And the way we cheat is that we basically train a whole separate neural network that we call a reward model. So as I mentioned,
For the second step, I chose this segment in the video about reinforcement learning from human feedback, or RLHF, because it plays a big role in making large language models like ChatGPT more helpful, safe, and aligned with what we expect from them. The idea behind RLHF is pretty straightforward. You fine-tune a model based on what humans prefer. So if a model gives two different answers, a human picks which one is better, and the model learns from that. Over time, this makes the AI more aligned with human judgment. But there's a problem. RLHF needs a ton of human feedback, especially if the training data is large or complex. That process is slow, expensive, and doesn't scale well. Andre Caparte, a well-known AI researcher, recently talked about a clever workaround. Instead of using actual humans for all the feedback, they cheated the system by training another LLM to simulate human feedback. The secondary model is trained to predict how a human would rate a response, and it's used to provide feedback for all the main model. Basically, they're using a neural network to mimic human judgment, cutting down the cost and speeding up the process. It's not perfect, but it's an interesting way to scale RLHF without relying solely on human labor.
it's actually going to go very slowly. It's going to be like, okay, let's define our variables, set up the equation, and it's kind of creating all these intermediate results. These are not for you. These are for the model. If the model is not creating these intermediate results for itself, it's not going to be able to reach 3. I also wanted to show you that it's possible to be a bit mean to the model. We can just ask for things. So as an example, I gave it the exact same prompt, And I said, answer the question in a single token. Just immediately give me the answer, nothing else. And it turns out that for this simple prompt here, it actually was able to do it in a single go. So it just created a single, I think this is 2 tokens, right? Because the $ is its own token. So basically, this model didn't give me a single token, it gave me 2 tokens, but it still produced the correct answer. And it did that in a single forward pass of the network. Now, that's because the numbers here, I think, are very simple. And so I made it a bit more difficult to be a bit mean to the model. So I said Emily buys 23 apples and 177 orange tea.
So this clip dives into a crucial concept. Tokens, the core building blocks of how large language models actually function. If we want to understand how these models think, we need to start here. In this video, Karpathy explains how LLMs don't read entire sentences or paragraphs like humans do. Instead, they break everything down into tokens. A token can be a word, a subword, or even punctuation. For example, the word unbelievable might be split into 3 tokens, un, believe, and able. Each token gets converted into a number that the model can process. Once the input is tokenized, the model's job is to predict the next token based on the previous ones. That's how it builds up responses 1 token at a time. It may feel like it's forming full ideas and but it's really just making a series of token predictions. Kaparte also touches on an important limitation here, the context window. This is the maximum number of tokens the model can remember at once. If your input or conversation exceeds that limit, earlier parts get dropped, which can make the model lose track of what's going on. So ultimately, understanding tokens isn't just a technical detail, it's key to understanding how LLMs process language, respond to us, and where their limits are.
Aggressive analysis here of all the ways that the models are kind of like falling short. I just want to make the point that there are some jagged edges here and there, and we've discussed a few of them, and a few of them make sense, but some of them also will just not make as much sense. And they're kind of like you're left scratching your head, even if you understand in depth how these models work. And a good example of that recently is the following. The models are not very good at very simple questions like this. And this is shocking to a lot of people because these problems can solve complex math problems. They can answer PhD grade physics, chemistry, biology questions much better than I can, but sometimes they fall short in like super simple prompts like this. So here we go. 9.11 is bigger than 9.9, and it justifies it in some way, but obviously, and then at the end, okay, it flips its decision later. So I don't believe that this is very reproducible. Sometimes it flips around its answer. Sometimes it gets it right. Sometimes it gets it wrong. Let's try again.
Here's another interesting example of how AI models can get things wrong, but in a very unique way. In this clip, Andre Caparte talks about what he calls jagged intelligence. That means large language models can be extremely capable in some areas like writing code or explaining philosophy, but then fail at something simple like comparing numbers. He gives the example of an LLM saying that 9.11 is greater than 9.9. At first, this sounds like a math error, but when you look deeper, it's not really about math at all. The model isn't reasoning like a calculator. It's using patterns and associations it learned from massive amounts of text. And what it's likely doing here is recognizing 9.11 not as a number, but as a reference possibly to a Bible verse like John 9.11 or even to the date 9/11. In its training data, 9.11 shows up in important, serious contexts more than 9.9. So it assumes 9.11 is more important or greater in a way that doesn't follow logical math. I think this is fascinating because it shows how these models don't actually understand the world they work off of, statistical associations, and sometimes that leads them to surprisingly human-like errors.
All you know is that this sequence of actions resulted in a loss, and this one produced a win. This kind of problem is called reinforcement learning. We don't know which actions were responsible, so we'll just penalize all actions we made in the loss, and reward or reinforce all actions we made in the win. This converts it into a supervised learning problem, just like we solved in the first part of this video. Actually, we can do a little bit better by penalizing later actions more, as the game losing the stake typically happens towards the end. and similarly for rewards. After training on 3,000 games, our agent has improved to play about as well as the opponent. You can see the score is pretty even. And after about 12,000 games, our agent figured out that hitting the ball with the corner of the paddle makes it go faster. Cool. And now it wins most of the time.
Here's another provoking insight from Steve Setz, this time about the challenges of reinforcement learning in AI. In this clip, he points out a strange problem. Depending on how the feedback is set up, the model might label all of its actions as a win, or the exact opposite, every action as loss. This happens because reinforcement learning relies on signals like a reward score to determine whether a behavior was good or bad. But if that feedback isn't specific enough, or if it's applied too generally, the model doesn't know which part of its behavior caused the outcome. So instead of learning, this move was helpful. It might just think everything I did was perfect or everything was wrong. This leads to overgeneralization, which can completely derail the learning process. It's a great example of how powerful but fragile reinforcement learning can be. The model's behavior is only as good as the reward signals we give it. So aligning those signals with human goals is one of the hardest and most important parts of training these systems.
Train LLM assistants like ChatGPT. We've discussed the first stage of that, which is the pre-training stage. And we saw that really what it comes down to is we take internet documents, we break them up into these tokens, these atoms of little text chunks, and then we predict token sequences using neural networks. The output of this entire stage is this base model. It is the setting of the parameters of this network. And this base model is basically an internet document simulator on the token level. So it can just it can generate token sequences that have the same kind of like statistics as internet documents. And we saw that we can use it in some applications, but we actually need to do better. We want an assistant. We want to be able to ask questions, and we want the model to give us answers. And so we need to now go into the second stage, which is called the post-training stage. So we take our base model, our internet document simulator, and hand it off to post-training. So we're now going to discuss a few ways to do what's called post-training of these models.
Lastly, we talk about is post-training and why it's essential for getting models like GPT to actually respond in a way that makes sense for users. Andrew Kaparte points out that pre-training alone isn't enough. During pre-training, the model is exposed to massive amounts of raw internet text. It learns general language patterns, grammar, and facts, but it's not trained to be helpful or even interactive. At that stage, it's just predicting the next word based on probability. So if you were to talk to a purely pre-trained model, it might respond in ways that are technically correct but not useful, or even not aligned with what you actually want. That's where post-training comes in. Post-training involves fine-tuning the model with more targeted objectives, especially using reinforcement learning from human feedback. This is where you teach the model to respond to prompts in a way that sounds helpful, safe, and human-like. For example, you teach it that when a user asks a question, it should provide a clear, helpful answer rather than just rambling based on next token predictions. So the difference is this: pre-training gives the model its raw knowledge of language, while post-training shapes its behavior. This is how we get GBT to feel conversational, cooperative, and context aware. Without post training, it would just be a really big autocomplete system, not something you can actually ask questions and get meaningful answers from. Alright, that concludes this week's video. Thank you very much for watching. I'll see you next time.